Okay, so we need to calculate the heat absorbed when converting 25.0 grams of ice at negative 12 degrees Celsius to steam at 112 degrees Celsius. So before we do anything else, first let's find out what this means by 25.0 grams of ice. We need to find out how many moles of ice we have. So we know ice or water, this is H2O. So we need to find out how many grams of H2O equals 1 mole of H2O so we can figure out what this 25.0 grams of ice is. So we go to our periodic table and H is right over here and the uh, atomic mass is 1.01, but we have two of them because it's H2O. So we take that times 2, so we get 2.02. And then we have oxygen over here, which the atomic mass is 16.00. So we take the 2.02 plus the 16.00, and we get 18.02. So if we just put grams at the end of that, 18.02 grams, that's going to equal 1 mole of water or of ice. So let's go back to our page. So we have 18.02 grams of H2O equals 1 mole of H2O. So our question mark, how many moles of H2O when you have 25.0 grams of H2O, this is going to be our data table. And we count everything to make sure it's mentioned twice. So we have moles of H2O, moles of H2O. Oh, I should have put H2O on there. And then we have grams of H2O and grams of H2O. So everything's mentioned twice, so we know we set it up properly. And we start with the row that has the question mark in it. And we take our known value, this 25.0 grams of H2O, put that over 1, and then we write a multiply sign and a fraction bar. And then whatever the unit of measurement is on the top of this fraction we just wrote, which is grams of H2O in this case, we're going to put that on the bottom of this next fraction bar, grams of H2O. And we're going to look up at our data table, and we're going to see that it mentions 18.02 grams of H2O. So let's write that down here. And then whatever's on the other side of the equal sign, we put on the top of the fraction bar, which is 1 mole of H2O. So now we can cancel out the units of measurement that are diagonally across from each other. So that would be the grams of H2O here, grams of H2O there. And that just leaves us with moles of H2O. And we go back and look at our question mark, and is that what our question mark's asking? Yes, moles of H2O. So we know we set it up right. So now we just have to multiply across 25.0 times 1 over 1 times 18.02. So that would be 25.0 divided by 18.02. And that's going to equal 1.3873473,918 moles of H2O. And that is how many moles are in of H2O are in 25.0 grams. So now that we know how many moles we're dealing with, we can go ahead and work the rest of the problem. Now, as you can see on here, on this graph, this shows the heating curve for water, for H2O. And here is 0 degrees Celsius. And as you can see, it plateaus. It starts out as ice down here. And as it heats up, we can see on the chart that when it's ice, the heat, the specific heat is going to be 2.06 joules per grams degrees Celsius. So this section right here, when it's ice, is going to be 2.06. But then when it gets up to and starts melting at 0 degrees Celsius, you see how this plateaus right here? So this is this is called the fusion, the heating point, the fusion heating point. So that's going to be this right here, and that's 6.01 kilojoules per mole. So this is going to be 6.01 kilojoules per mole. And then once it finishes melting, then it goes up, and while it's in its water phase, and you look on the chart to give you the specific heat of water when it's in its water phase, and that's 4.18. So this entire thing is going to be 4.18 until it gets up to 100 degrees Celsius and it starts vaporizing. It starts turning into steam. So when it starts vaporizing and turning into steam, we have the heat at the vaporization point, which is 40.7 kilojoules per mole. So 40.7 kilojoules per mole. And then once it gets finished turning into steam, then the temperature starts increasing again, and that's when it's steam. So we know the specific heat for steam is 1.87 joules per grams times Celsius. So this is going to be 1.87. So I just wanted to show you this so you could get sort of a visual of what's going on with all of these specific heat requirements. So now let's take what we know and solve the problem. Now we have 25.0 grams of ice at negative 12 degrees Celsius, and then it's going to go up to 0 degrees Celsius before it starts melting. So we know the specific heat. We have to plug this into this formula or the heat that you absorb, sorry, when we plug this into the formula is going to be the mass of the ice times its specific heat, so we know down here the specific heat of ice is 2.06 joules per grams times degrees Celsius times the change in temperature. And the change in temperature is going to be this negative 12 until it gets up to 0. So that's going to be a 12-degree change. And we know this mass in the specific heat formula is going to be the 25 grams. So we have, for the first part of this, we have 25.0 grams times 2.06 joules per grams times degrees Celsius times a change in temperature, which is 12 degrees Celsius. And that's going to give us that first part of the graph when the ice is warming up until the point that it melts. So first, let's go through and cancel out the units of measurement that we can cancel out. So we have grams right here, and then we have grams on the bottom of this little fraction bar. So these are diagonally across from each other, so we can cancel out the grams. And then we have Celsius over here on this side, degrees Celsius, and we have this degrees Celsius on the bottom of this fraction bar. So those two can cancel out. And that just leaves us with joules for the units of measurement. So now we just have to multiply 25 times 2.06 times 12, and that's going to give us an answer in joules, because that's the only unit of measurement we have left. So that's what we carry through. So 25 times 2.06 times 12 is 618 joules. So that's the very first part when we're heating up the ice until it's hot enough to melt at 0 degrees Celsius. So we're going to write this 618 over here. 618 joules. So that's the first part. Now our second part, if we go back to this graph, our second part is the work's already kind of done for us. It tells us the entire time it's at 0 degrees Celsius, the amount of heat of fusion is 6.01 kilojoules per mole. So 6.01 kilojoules per mole. And now we have to go back and remember when we figured out how many moles of the ice we have at the beginning. So we have 1.38734733918 moles. So let's write that down. So if we have 6.01 kilojoules per mole, then how many kilojoules do we have if we have 1.38734733918 moles of H2O? Well, how are we going to write this in our data table? Well, we can take the 6.01 kilojoules is going to equal 1 mole of the substance, because you can take this little fraction bar, kilojoules over mole, and you can change that into an equal sign. So we can say 6.01 kilojoules equals 1 mole of H2O. So this would be your data table. And if we start with the question mark row, we're going to have 1.38734733918 moles of H2O over 1, and then a time sign. We're going to put the moles of H2O on the bottom, and the other place it mentions that we have 1 mole, and whatever's on the other side of the equal sign goes on the top of the fraction bar. So we have the 1.38734733918 times 6.01, and we can cancel out these moles of H2O, and that leaves us with just kilojoules. So if you multiply these together, you're going to get 8.3379578.247 kilojoules. And so now we have how many kilojoules are given off while this ice is melting at 0 degrees Celsius. So we can write this over here. Now we need to find out what the amount of heat is going to be now that the ice is melted into water from 0 degrees Celsius to 100 degrees Celsius, because at 100 degrees Celsius it starts to turn into steam. So the temperature change in this would be from 0 to 100, so that would be 100 degrees Celsius is the change in temperature. And remember now the formula is the amount of heat is the mass times the specific heat times the change in temperature. So this 100 degrees is going to go right here where the change in temperature is. And the mass is, we're still dealing with 25.0 grams. And then the specific heat number, we're going to look down here, and when the specific heat of water of H2O is in the water phase, it's 4.18 joules per gram Celsius. So 4.18 joules per grams Celsius. So now we know the formula is going to be the amount of heat absorbed equals the 25.0 grams times 4.18 joules per grams Celsius times 100 degrees Celsius. So before we do any math, we need to cancel out what we can. So we have grams here and grams here in the bottom of this fraction bar. And we have Celsius in the bottom of this fraction bar and Celsius right here. So that just leaves us with joules. So now we just have to take 25 times 4.18 times 100, and that is going to give us 10,450 joules. So let's write that down here on our little list we're keeping. 10,450 joules. Now we have gotten up to 100 degrees Celsius where this water starts turning into steam. So that would be the heat of vaporization. And that's 40.7 kilojoules per mole. So if we have 40.7 kilojoules is for 1 mole of H2O, then how many kilojoules are we going to have with the moles of the water that we have? And remember, the moles that we have that we calculated is 1.38734739118 moles of H2O. So we have our data table now, and we start with the known quantity. So we have 1.38734739118 moles of H2O, and we put that over 1, and we do a multiply sign and a fraction bar. These moles of H2O we repeat on the bottom. And if we look up at our data table, we have written 1 mole of H2O, so that's going to be a 1. And whatever's on the other side of the equal sign, we put on the top of the fraction bar, which is 40.7 kilojoules. And now we can cancel out these moles of H2O because they're diagonally across from each other. So now we have 1.38734739118 times 40.7, which gives us 56.4650388.463 kilojoules. So let's write that in our list that we're keeping down here. 56.4650388.463 kilojoules. Now for our final one, we've turned this ice all the way into steam, and it turns into steam at 100 degrees Celsius, but we need to go up to 112 degrees Celsius. So the change in temperature for this part is just going to be 12 degrees Celsius because we're going from 100 to 112. So the difference between that is 12 degrees. So we are going to once again use our formula. And so the mass is going to be 25.0 grams. The specific heat, if we look down here at our chart where it says steam, the specific heat is going to be 1.87 joules per grams Celsius. And then the change in temperature is going to be 12 degrees Celsius. Now we can cancel out these units of measurement that are diagonal from each other. So all we have left is the joules. So if we take 25.0 times 1.87 times 12, we're going to get our answer in joules for how much heat. So 25 times 1.87 times 12 is going to give us 561 joules. And so let's write that in our list. And I ran out of room, so I'm going to write it at the top. 561 joules. Now, all we have to do, now that we've made our list of all of the different steps that the H2O needs to go through to go from ice at -12 to steam at 112, we have this little list of all the different amounts of heat at all the different steps that we had to take, and all you have to do is add them up. But if you look at this, what problem would we run into adding these up? Now, if you said 2 of these are in kilojoules and the rest are in joules, you would be right. So we need to convert either the joules to kilojoules or the kilojoules to joules, just depending on how you need to answer your question. So we're just going to convert the kilojoules to joules and add them up. But you can convert the joules to kilojoules and add them up too if your answer needs to be in kilojoules. So first, 8.3379578.247 kilojoules. Kilo means 1,000 joules. So if we have, if 1,000 joules is 1 kilojoule, and 1,000 has 3 zeros in it, all we need to do to convert kilojoules to joules is to move the decimal point over 3 times. Because see, there's 3 zeros in 1,000. So we take this decimal point and we go 1, 2, 3, put the decimal point there. So your answer is 8,337.9578247 joules. And then we need to do the same thing for this down here. We have 56.4650388.463 kilojoules. So if we move the decimal point over 3 places, then we're going to get 56465.0388.463 joules. So now that we have these values, we can just add up 561 joules plus 618 joules plus 8,337.9578247 plus 10,450 joules plus 56,465.0388463. And if we add all of these up, that's going to give us the amount of heat in joules that is absorbed when we go all the way from negative 12 degrees Celsius all the way up to 112 degrees Celsius. That's going to give us 76,431.996671. And if we look at our original problem, we have three significant figures here. So we can round this to 3 sig figs, which would be 76,400, or you could also write it as 7.64 times 10 to, oh, that's the second, 1, 2, 3, 4 times 10 to the fourth. And that's going to be in joules. Now, if you need this in kilojoules, all you have to do is just move the decimal point 3 times backwards, and that will give you 76.43, and it's 431.996671 kilojoules, which again we need to round to 3 sig figs, so that would be 76.4 kilojoules. And that's it. I mean, I don't mean that's it, that was long, but it's just basic math, multiplying and adding, but it tends to confuse people because it just takes so many steps you think you're doing it wrong. But you're not doing it wrong. You have to do a different specific heat for every phase change, and at every phase change, you're going to have the heat of fusion and the heat of vaporization you have to add in there as well. So I hope that makes sense. If you have any questions about this whatsoever, please don't hesitate to call.